Okay, this section is about the method of undetermined coefficients. And we use this method to find the particular solution, which I'll explain below, particular solution of a non-homogeneous second order linear differential equation. So remember, in the previous couple of sections, we studied uh, homogeneous second order linear differential equations, which is the same form, but there the right hand side is zero. So if the right hand side is zero, we have it ay double prime plus by prime plus cy is equal to zero, then that's a homogeneous linear second order. But if the right hand side is a function of t, where remember y prime is dy by dt, and y double prime is d square y over dt squared. So we're assuming that the independent variable is t. If it's x, if the independent variable is x, then this will be f of x. So in general, if the right-hand side is not zero, but a function of x, then that's a non-homogeneous second order linear differential equation if it has this form. So the steps involved in solving such an equation are: we first find the solution yh of the associated homogeneous equation, where we just rewrite this equation and have the right-hand side zero. And then we solve this homogeneous equation by the methods which we learned in the previous two sections. And then we find the particular solution by assuming it of the form similar to t power k f of t. So the particular solution is usually of the same form as this function f of t, and I'll discuss below what the same form means. But uh, if by just writing it of the form of f of t, you see something that is repeated in the solution of the homogeneous equation, then we multiply that form by the lowest power of t. So the lowest power of t would be 0. So t power 0 is just 1. So if all of f of t terms are different from the homogeneous equation solution, then we don't multiply by any power of t. But if there is some matching term, then we multiply by t. And if still there is some matching term, then we multiply by t squared. And we keep going higher powers of t until there is no matching term in the particular solution to the solution of the homogeneous equation. And this will become more clear once we start working some examples. Okay, so here are some examples of particular solutions. So particular solution form depends on the f of t, which is the right-hand side. So if the right-hand side is a polynomial of degree n, then usually the particular solution will also be a general polynomial of degree n. But again, as I discussed above, it may need to be multiplied by some power of t so as to make sure that all the particular solution terms are different from the solution of the associated homogeneous equation. And then if the particular solution is a polynomial of degree n times e power rt, then the particular solution will be again general polynomial of degree n times e power rt times t power k. And if the particular solution is of the form e power at sine bt or e power at cos bt is what I meant, then the general solution, then the particular solution takes the form GEAT sine BT plus HEAT cos BT, and again times t to the k, where g and h are constants. So note here that the form of ft could just have EAT sine BT, but even then we'll have both sine and cos terms here. And also if it's just EAT cos BT, we'll have both sine and cos terms here in the particular solution. Okay, so now let's look at a problem. Find the particular solution of this equation. So you see, we have almost the same, but instead of having 0 on the right-hand side, we have something else. So here, the step one is to find the solution of the associated homogeneous equation so as to make sure that we don't have repeated terms in the particular solution. So we'll write the associated homogeneous equation is, let's be just the same thing but with a 0 on the right hand side. To 0. Okay, so here we just use the normal process by writing the auxiliary equation. And so let's see. Okay, let's just write this. So the auxiliary equation for this one will be r square minus 4r minus 1 is equal to 0. And let's see what r will be. So now remember, we have a constant on the right hand side. So this is the f of t. In this case, f of t is 21. And as we said here, if it's a polynomial of degree n, so 21 is just a polynomial of degree 0. So the most general polynomial of degree 0 is a constant. So in most cases, the particular solution will just be a constant because that's what this f of t is. But if the general solution also contains a constant, then we may need to multiply the particular solution by a power of t. So that's why we are finding the general solution of the homogeneous equation. By general solution, I meant the solution of the homogeneous equation. So let's see what this will be. So this will give us r is equal to, let's use quadratic formula. So we'll have 4 plus minus square root. The square would be 16 minus 4 times 1 times 1, so that's just 4. So we already see that 16 minus 4 is 12. So we are getting two distinct roots for plus minus square root 12 by 2. So we get two distinct roots, distinct and real roots. So that is case 1. So general solution of the homogeneous equation is of the form. In this case, we know we'll have y is equal to CER1T. So this is case 1, R1 and R2 are distinct. Okay, and R1, R1 would be the first of these roots and R2 would be the second of these roots. And obviously we can see that none of them are 0. Therefore, so we have two terms here. C1ER1T is one term and C2ER2T is the second term. So both of these, since both the roots are non-zero. So right now this is a solution of the homogeneous equation. So maybe we should write it as y of h. This is the solution of the associated homogeneous equation. Okay, so since both roots are non-zero, so none of the terms in YH is a constant. Thus, YP in this case would just be the most general constants, let's say C. Okay, so now let me explain this a bit more here. So why did we go through this solution of the homogeneous equation? Okay, the main thing here is that the right-hand side was a constant, and we wanted to see if we can just write the particular solution as a constant, which we can do as long as none of the terms in the solution of the homogeneous equation is a constant. So now let's see, how could a term in the homogeneous solution be a constant? Well, that could happen if one of the roots were to be zero. So here we can see that none of these two roots will be zero, but let's say one of the roots was zero. Let's say R1 was zero. So then this would be C1 e to the 0t, and e to the 0t is 1. So that would just be C1. So in this case, one of the terms in the homogeneous solution will be a constant, and therefore we can't say that yp is also a constant because this should not match this. So in this case, we'll multiply by a t here. So instead of yp equal to c, we'll have yp equal to t times c, assuming that there is no t times c term in the YH. So here, once we made sure that we don't have a constant term in the YH, we can now safely say that YP is constant. And now this constant needs to be determined. So now the job of the homogeneous equation is now done. Now we go back to the original equation. So substituting this in the given equation, not in the homogeneous equation, but in the original given equation. Get. So wherever you have a y, you substitute c. So think of this as now yp, and we just substitute a c. So I'll just copy this equation. And instead of y double prime, we will have c double prime. For c prime minus c is equal to 21. And now derivative of a constant is 0. So this part, these two are 0. So these two, the c second derivative will also be 0. First derivative of constant is also 0. So we'll only have negative c is equal to 21. And that will give us c is equal to negative 21. So yp was c, so it means yp is negative 21. Okay, so now here I wrote find the particular solution. The correct thing is to write find a particular solution. And the reason for that is that, okay, we found this particular solution, negative 21. Anytime you find a particular solution of the equation, then the particular solution plus the general plus the homogeneous solution is also a particular solution. So let's write this thing here. In fact, we should have written this at the end. The solution. So now we are not talking of the homogeneous solution or the particular solution. In step 1, we talked of the solution of the homogeneous equation. In step 2, we find, here also we should say find a particular solution. And then we talk about the solution, which means the complete solution, not any of the two parts. The solution of the given equation is y is equal to yh plus yp. Y is equal to yh. And I'll mention why I did not write this thing before. Plus yp. Okay, so this is what you will do in real life. You will find the YH, you will find a YP, and then the total solution will be YH, Y is equal to YH plus YP. But in the software, all the problems I saw, they don't ask you to write the total solution. They just ask you to find a particular solution. So that's why I kind of stopped over here. But this is the complete solution, which you will be doing once you do in real life. But this is just a tiny step. The main step is to find a particular solution. We already know how to find the homogeneous solution. And once you find particular solution, it's just a question of adding the two, which is not a big deal. So here, say yp is negative 21 is what they're looking for. So let's now, this one will be negative 21. Okay.